This is the first of two product and technology showcase demonstrations today, and I'll be picking up on the themes that Claire talked about earlier. I'm going to show examples of how our customers are using automation and rules to manage their authoritative data. And essentially this is location master data management in action. Now first I want to show one Spatial Management Suite and one edit being used to cleanly and safely edit Ordnance Survey Island reference data. So one Spatial Management Suite helps you plan data updates to your production data. You plan a job, you have an editor that makes it updates to that data, and then they submit it for validation, conflict resolution, and finally integration into the live data if it's all correct. This means that you have control over your data. You can have lots of editors editing the data at the same time, and it's always ready to publish. So here's one plan. We're going to plan a job to do for an editor in this area. So we've got some change intelligence that there's some changes have happened here. And I'm going to plan a job extent, where does the edit need to happen, provide some information about the type of job, assign it to a user or a group. And this means that those users can then make the edits. The edits will be done in the one edit application. And that could be out on the field with GPS or capture devices, could be in the office with imagery or even photogrammetry. So now that job's been created and assigned to the user, now I'm going to switch to the one edit application. So as a user, this is my view. I've been given that job assigned to me, and I'm going to activate that job, which means prepare it, take it out of the database and provide it to the user as a package of data that I can now edit. That once I've got that downloaded, I can work on my device, possibly offline, to make my edits to the application. And on the server, one Spatial Management Suite is working with a database to keep a record of the data, the version of the data that I downloaded, and that can help us to manage other users editing at the same time. So I'm downloading this data, I'm opening up inside one edit, and the one edit application is now going to allow me to make some edits to this data. I'm going to make a couple of just example edits. So there's a wall inside a building. I'm going to delete that object, and then once we've deleted that, I'm going to create a new building. So I'll create a new building in this garden here. Now I'm just doing this by roughly clicking the building outline. Typically I'd be using a device to capture the location of the building, or use imagery to trace around, or techniques like that. So I've created the building, and I also need to define not just the footprint, but in this data model we have a secondary address point within it. And you can see top right there are various rules that are failing. So as we edit the data, it becomes correct. So I need to define the attributes, I need to define the right geometry, and as we go through and make those edits, you can see those rules, that list of failed rules top right is reducing, so that we end up with correct data. Now I'm going to leave this with one error because I want to see what happens if I submit data that's not completely correct. So I've created a building, and I'm going to now submit those changes back to the server. So I can open the one edit work list, and I can select the job and say upload, and I provide the information required for this job update, and then submit that back to the server. What gets submitted back to the server is a change only update package. So here are the changes that I have made as my user, and that gets sent back to the server, and it gets loaded into the database, but not the live data. It gets kept in a workspace, which means it's safe, ready to be validated and checked for conflicts and checked for validation. Now, because I left an error within my data, this job has been stopped. It said it's invalid, and now I need to correct that error. So the system has generated me a new job ready to receive the data and the reasons why there was a validation error. And that can be, I'm going to pick this up, it could be a QA team that was picking this up. I'm going to download that job and open it, and we're going to now correct that error. So first of all, I'm going to confirm, and we have the same rules running both on the client side and the server side. So I can run the rules here, and this would have told me, and this did tell me, that there was going to be a problem when I submitted. I can run that and confirm it again. And I can also check, well, what did the server tell me was the problem? And we can see it's the same rule that's causing the same problem to the same feature. So there's the same rules running client side and server side. So I'm going to go and correct this. Now the reason this has failed is because my rules state that a building must sit on top of an artificial surface polygon, which is part of the skin of the earth. And it must be the same size. So what I need to do is generate an artificial polygon the same shape as my building. And the easiest way to do that is to use the geometry of the building. So I'm going to then create a new artificial surface by copying the building geometry, and I can set the attributes on that, because it's telling me, again, my rules are telling me that actually there are certain attributes that need to be specified for this to be valid. So I'll set the attributes to make this correct. And the other thing it's telling me is that I've got an overlap between my two surfaces, the garden that I'm in and the artificial surface that I've just created on top of it. So I need to punch a hole in the garden so that skin, I get a coherent skin of the earth. And then once I've done that, then I can check that my building is correct. I can check and revalidate the artificial polygon, and I can check the building and revalidate the building and make sure that all these various parts are correct. So that's now telling me that my data is now valid, and I can check my rules, and I can check across the whole, all of the changes I've made by running the validation on just the changes in this data set, and this is telling me, yep, this is all correct. So the client side, I've got a good confidence that when I submit it, this is now going to be accepted and it's going to be valid. So now I can go back to my work list and I can submit that change of the downloaded correction job, and I'll provide the metadata again, and this will send the changes back to the correction job, which will, when received, will run the validation again. And if that passes validation, then that's merged into the original job. So you can see my original job on the right, it's stuck, that's paused and invalid. I've made my new changes and I've submitted those, and those will now be received by the server and checked. And if they pass validation, then that job will move into a completed state, and then the changes will be propagated up into the original job that's paused, and that can then be checked. As well as checking validation, we're also checking for conflicts. So if other users are around, they're able to edit the same data. We don't lock people out of that data. But we need to check that no one has come in and changed those same features under my feet, otherwise I might be trampling their edits. So if the data is valid and there are no conflicts, then both the correction job is completed, and then the original data update job can go through validation. It's now being automatically validated, and then that data validation, that data update job will then go to completed as well. And now that means that both of those jobs are now complete and the data is live in the database. So now I go back to my planner view and I can have a look at the live data, and I can have a look at the job status. The job status is set to completed, and I can then, if I move that job extent out of the way, we can see underneath we've got the new building has been added, and I've got my wall is no longer visible. And so we've got a complete cycle of data updates with rules and automation, and we can see now that that's how we can get clean and coherent data, and you can see the attributes there for the updated data. So we've produced the updates, but only if the edits are clean and coherent, and that's how we generate our authoritative data that can be published now at any time because it's always correct. Now we're going to move on to OneIntegrate, which is OneSpatial's rules engine, and we use this for enterprise integration and data quality tasks. OneIntegrate helps to work on the data that we've just talked about, the master data, the authoritative data, and how we can use it in combination with other information. And we can apply rules to validate and fix the data, as in cleanse things. We can apply rules to match and merge different data sets, so integrate things. And we can also apply rules to improve and analyze the data to enhance things, and that adds additional downstream value. So here on OneIntegrate, I've got a session running on some data. This is data, in this case, from Ordnance Survey Northern Ireland. And I'm doing a series of tasks. I'm doing some data validation tasks, and this data is both 2D and 3D data that we're working on here. 3D is a new capability that we've added to OneIntegrate, and we'll have a look at the data in a moment. And we're doing a series of validation checks, and for each validation check we're getting some conformance, and then we're doing some data enhancement. So let's have a look at what's been happening. So this is the data that we've been working on, and we can see that we've got the 2D footprints in orange there, and in green we've got the 3D buildings. And the 3D buildings have come from a number of different sources. Some have been extruded up from the 2D, some have been captured separately, some from additional processing and from LiDAR, and all sorts of information has come in to generate these 3D buildings. We're interested to see how the two sources of data, how they match and how they relate to each other and whether we can improve one from the other. So first we do some basic validation. For example, are the 3D solids valid themselves on their own? Yes, they are, 100%. Then we can do checks for things like overlapping buildings, but the things that we're interested in for these purposes are initially the matching between the 2D and the 3D data. So when we did an exact match between the 2D and the 3D data, and we said, show me if there is any slight difference between the flattened version of the 2D and the flattened version of the 3D and the 2D data, then there were subtle differences. Every single feature reported a subtle difference in how the geometries are encoded. And that's not surprising because they're different data, they're structured differently, and therefore we have to be a bit more tolerant than that. So then we run a rule to say, well, okay, if we're tolerant to within 30 centimeters, then how well do we match? And now we have a small, rather than them all failing, only 20 of them fail that match. And we can step through them. And then we were even more tolerant. We said, okay, within 1 meter, what are the differences within 1 meter? So let's step through those differences. So here we can see all of the differences in the data where there is more than a meter difference. And some of them are because of positional offsets, and some of them are because of real world change. So here, for example, we've got a building that's been knocked down and replaced by smaller ones, or actually, in reality, because we know about the sources of data and we know about the provenance and when the data was captured, this was some smaller buildings have been knocked down and a larger building put there in its place. So that's a real world change. So there are a number of different reasons why, and sometimes it's just because of the subtle encoding. If I turn the perspective off, it's the subtle differences in the encoding between the 3D geometry and the 2D version. Now what we're interested in is, if we have a look at the tasks that we did, we then said, well, actually let's have a look at where there is a difference based on the positional accuracy or the positional location of the features. So here, for example, we've got, now this is something that we've introduced for the purposes of the demo, there is an offset. If we turn it into 2D, you can see that more clearly. There's an offset between the 2D version and the 3D version. And so we want to see if we can automatically improve one data based on the other. Now here we know that the positional location of the 3D data is more accurate, and therefore we want to shift the 2D data appropriately. But there are also differences in the encoding. The 2D data, the buildings, each separate building captures a separate geometry, a separate object, but in 3D that's one single structure. And so we need to tolerate that sort of ambiguity in the encoding, but be able to recognize that these 3 buildings in 2D together are equivalent of that 3D building. And we can do that using rules. So what we can do is we can generate automatically some shift vectors by comparing the 2D and 3D data and treating them as a cluster of objects, and find, is there an equivalent feature whose 2D footprint is very similar to me, very similar size, very similar shape, but is simply offset. And from that we can automatically generate shift vectors, and once we have that, then we can shift the buildings from 2D to 3D. So if I step between, you can see that 3D building shifting underneath the 2D building. It's still there, it's underneath. So then we can improve the positional accuracy, and if we go back to the original session with the statistics, we can see that the match within 1 meter was 81%, and after automatically shifting it, we can match to now 89%. So that's much higher quality of data. And what we've done is we've improved one set of data from the other. What's important as well is we've not shifted any of the other data around it. Where there wasn't a positional shift required, then that data hasn't been moved, and we've not incorrectly reduced the quality of the surrounding data. Now there's another use case we want to do, which is generate floors within a building. And there are various reasons why people want to do things with their 3D data. Sometimes it's taxation purposes, sometimes it's environmental, so being able to analyze the carbon footprint of a building or the heat efficiency. In this case, we're interested in generating the floors for the building to help with taxation purposes. So what we're going to do is we can automatically apply rules to split these buildings up into separate floors. Now to do that, we will depend on various bits of information. So for example, if we want to split a building into floors, then we want to exclude the roof surface. And we do have information about the specific roof surfaces. If we turn those on, then we can see that we know where the roof is. So we don't want the floors to extend into the roof. We want to go from the bottom of the roof to the ground and split those into floors. There is information on the 2D polygons about what type of buildings these are. So these are classified as residential, whereas these over here are classified as non-residential or commercial. And therefore we can work out a number of floors. Now, the 2D buildings have information about them, about how many floors they should contain, and not all of them are populated. If they're not populated, then we can infer it. We can say, well, this is residential. We'll assume it's probably a 3-meter floor height on average. If it is populated, we can use that floor height that floor height information. And so what we can do is we can generate the internal floors for the buildings automatically. So if we go down to the part in the session where we've generated the internal floors, and I'll turn the roofs off here, then we can see that we've automatically generated floor polygons. Now, in some buildings it's the entire floor. For other buildings we have floor plans available, and we've pulled in that floor plan information that's down there on the ground, and we can use that floor plan information with height information to generate not just internal floors but internal rooms within the building by splitting up this 3D building that we took in the first place, and we've enhanced it and generated additional information which can now be used for various purposes such as taxation or environmental analysis. Finally, I want to show One Data Gateway. All of the rules for validation and enhancement that we've seen in One Integrate are made available in a controlled way to users via an easy-to-use cloud portal. And this can be used for all sorts of data automation use cases, for data validation, data improvement and enhancement, or data acceptance and ingest. One Data Gateway allows the administrators to grant users access to different sets of rules, and these are called projects. You can see a set of them here. By allowing access to certain rules, you can also allow monitoring and analytics on the uploads that are made. Now, here's one example. This is for a police records management system. Rules are used to check each record against a corporate gazetteer, and if the unique property reference number in the police records management system isn't correct, then the system can automatically validate it and improve it with an audited change. This is an example of how a user will then upload their data and run it through the process once the administrators allow them access. They will upload the data, it will check that it's the correct structure, and then it will apply these rules automatically. In this case, we are checking against one, or it could be multiple, reference systems in the back end that are used to check and compare the data and then also make an improvement. Here you can see there's a low level of data conformance, and then there's a cleanse operation that results in a higher level of data conformance, and it's now meeting the corporate standards. The results can now be downloaded, and because the UPRNs are being corrected against master data, it's now possible to start linking data sets for improved data sharing and operational analytics. That's part one of the product and technology showcase, and later Bob will be showing the second part of the showcase on how we exploit and make use of that authoritative information.